So as we're waiting, I'll just begin to introduce Jess. So Jess is an associate professor of geophysics at the University of Oxford, and as a COMET scientist, she predominantly works on earthquake mechanics, signal processing. Her research interests include physics-based earthquake forecasting, blind source separation, aseismic slip and fault structures, and then also earthquake source properties. Today she'll talk through some of our recent research. Hopefully I haven't missed anything important there, Jess, but we've got about 23. We're expecting a few more, so you just take it away whenever you're ready.
Sure. Yeah. So what I want to talk today is about physics-based earthquake forecasting and how we can change some of the ways that we can do earthquake forecasting. And kind of progression that we've seen through the years and maybe where we can start to think about going as those of us who work more on the physics of earthquakes. And so the goal is to say, well, I have a bunch of observations and I want to use a physical model, and in fact, a relatively detailed physical model, in order to use those observations in order to estimate earthquake hazard. But if you'll humor me for the first 10 or so minutes, I'll give you a little bit of perspective of how this works, because I've certainly changed dramatically the way I think about earthquake forecasting in the past 5 years. So long-term earthquake forecasting is dominantly empirical. So to first order, we often say that earthquakes occur where past earthquakes occur, and earthquakes occur on faults. And if you're in a mature and kind of really dynamic, really active fault zone, that's a pretty good estimate. And in fact, it's going to be hard to do much better than that if you're thinking about really long-term forecasting and planning. However, over the past decade or so, people have started to incorporate more and more physical constraints into these models. And so you have things like the grand inversion and associated with usurp3, where you say, no, I know where the faults are and where the past earthquakes are, but also I know something about earthquake distributions, long-term slip, and all fault deformation. And the data over the past years has just exploded. And so that's led to increasing evidence that we could use lots more subtle information in our earthquake forecasts. So these plots, while rather unassuming, are really exciting results that suggest that maybe you can use laboratory acoustic observations in order to predict the time of the next lab quake. And also that things like deep learning can look at earthquake waveforms and say, oh, this one's a foreshock and this one's an aftershock. And so this seems really exciting. We'd like to continue to use all of this. But not only that, there's very much a need for changing the way we forecast earthquakes. And that's because we often find ourselves in scenarios where earthquakes are occurring in regions where they really haven't before. And so this could be things like induced seismicity, so you talk about CO2 sequestration, or wastewater injection, or you're talking about geothermal. You can't really use a past empirical set of earthquakes to forecast the future because there isn't a past empirical set of earthquakes in that region. And likewise, even if you go to really well-established regions, you get to scenarios like what's my nightmare scenario and something that's kept me up at night. And that's when you think about slow slip events, so you think about earthquake swarms. So the example here, this is GPS motion prior to the Iquique 2014 earthquake. And here you see relatively large displacements in the GPS. You also saw seismicity increasing prior to that. But now most of the time when you see that sort of slow slip events, or you see a seismic swarm, most of the time that leads to nothing. But some of the time it leads to a magnitude 8 or a magnitude 9. And so this puts us in a really awkward position where you might say, okay, well, if I saw a slow slip event that was very different to past events, technically I wouldn't have a lot of justification for saying that that's hazardous. But in practice, it would be very much a cause for concern among scientists, I think. And so right now, we have to respond to that. We have to say, I don't know how dangerous this is, or give some sort of justified estimate of how we can assess that. But what I'd like to know is what could we do in the future? What could we do 20 years from now, 10 years from now, or even earlier to be able to say, okay, there's this slow slip event. How can I use a physical model in order to decide whether that's dangerous? And so for these new physical scenarios where we have really limited empirical data, we want a more physical model of earthquakes. So we want to be able to say, look, this is my fault conditions. These are my fault properties, my stress conditions, my rheology. I'm going to use my observations in order to infer the conditions on the fault. And then I'm going to use those conditions on the fault in order to estimate earthquake likelihood and hazard. And to first order, what we're going for here is to say that we'd like our earthquake forecasts to be a little bit more like weather forecasts, or at the very least like hurricane season forecasts. So if I'm going to say that, that's a nice goal. I want to go from observations via a really detailed physical model to hazard, rather than kind of empirically from observations to hazard. A good question is that possible? Is that even plausible things to do? And if you had asked me 5 years ago, I would have said probably not, right? Maybe the Earth is just too complex. There's too much variability and stress. There's too many unknowns rheologies. And to first glance, if you say, okay, well, what if I start an earthquake in a stress field that looks like this red and blue thing? So red is high stress, blue is low stress. I start an earthquake here. Is it going to rupture? And if I want to know if that particular earthquake is going to rupture and how big it's going to be, I need to know the details of this fault distribution. I need to know millions of parameters to specify that. But in practice, I don't really care if it's this earthquake or a relatively similar one. All I really care about is what's the likelihood of a big one, right? And so if I wanted to know that, maybe I don't need to know every detail of the fault distribution. Maybe I just need to know a few parameters of the stress distribution. Maybe I just need to know the mean stress on the fault or the standard deviation in stress on the fault. And so I've specified this fault distribution with 3 parameters, so there's not more than 3 that I can specifically know. And that seems like a much more reasonable number. So let's then ask, okay, how many parameters do I need to know about my fault system, and how many can I know? So we can start making a list. What kind of fault properties and conditions would I like to know? And I might like to know, okay, orientation, some sort of complexity, some statistics of the frictional properties. Is it on average velocity weakening or strengthening? I might want to know stresses, like what's the average stress, what's the standard deviation in stress, maybe something about the roughness and the pore pressure. And so here you get to kind of 10 or 100 parameters, kind of statistical parameters of the fault properties. And so if I want to know those 10 or 100 parameters of the fault conditions, I'm going to need at least 10 or 100 observations. And so the next question is, can I make 10 or 100 observations? Different types of them, because I need 10 or 100 independent observations. And so here we say, okay, well, maybe I can know the fault traces at the surface. I can know earthquake rate, B value. I can know things about variation in seismic wave speed. I can think about subtle properties of the earthquakes, maybe directivity, complexity. I can think about earthquake stress drops, orientations, and focal mechanisms. And so actually, when I think about this actually seems reasonably plausible, right? So maybe I can get 10 or 100 properties. And so here, if we think about this, we think, okay, well, if I'm going to make a generalized physics-based earthquake forecast, something like a weather forecast, I need to know this many parameters, and I might be able to get enough observations to do that. And so that's this third bar here. The only trouble is that we need to somehow map these fault parameters and conditions to all of these observations, right? And we don't have a set of empirical observations in order to do that. And so the next challenge is we're going to have to make a model, some sort of physical model that can map the fault conditions to the likely observations. So something that can map the average stress to the average B value on the fault, for instance, and map all of these different properties backwards and forwards. And of course, the last thing we're going to need to know is we're going to need to know when we're wrong, when this physical model that we've come up with is actually completely inapplicable to the system and we need to throw it away. Now, I'm not going to address that last one here. In this talk, I'm going to spend most of the time on this second challenge in physics-based forecasting, and that's making a model to map between parameters and observations at hazard. And then I'll give you some ideas of observations and how we can start thinking about changing our observations and how we are changing our observations in order to accommodate rapid physics-based earthquake forecasting. So let's talk about the model. So we want to build a model that can say, I have a bunch of fault parameters. These are the physical properties of the fault. They might be things like the rheology, the stress, and so on. And I need to be able to map these physical properties and conditions. And I estimate the hazard, the likelihood of a large earthquake as a function of those fault parameters. And I also need to be able to estimate the likelihood of any observation, so any kind of specific features I expect to observe, so that I can go backwards and forwards from the fault properties. And so if we're going to go from these fault properties to the observations, we're going to have to make a model that we can run lots and lots of times. So if we want to explore many parameter space, we would need at least billions of simulations, probably more like trillions or more. So we had darn well better be able to run these things fast. But of course, the model has to be also capture key physics of earthquake physics. And we don't know exactly what we need in order to capture here in order to be correct enough. And so I spent a while thinking about how to do this, and eventually decided to stop faffing around waiting for the correct model. And instead, I'm just going to build a proof of concept model and see if we can make this thing actually work. And I'm going to add here that maybe this kind of building model and mapping between all of these different things is actually a really powerful way forward in terms of thinking about testing physical models. Because this is one way to know if our model is correct, if we can match a lot of these observations, and if we can match a lot of these. So in the next 20 minutes or so, I'm going to define the model. I'll show you it's an energy really simple, probably less than that actually, but define a really simple energy-based structure model. We're going to run a bunch of simulations with this physical model, and then we're going to try to make it practical so that we can go back and forth between fault parameters, observations, and hazard. And that, however, is a little bit of ongoing work. So let's spend a little bit of time defining what's the simplest but plausible model of an earthquake that I can come up with. And I think the simplest model is probably an energy-based approach. And so this, conceptually, I think is relatively uncontroversial. And it's going to say that, well, earthquakes are driven by release and stress, right? So we're going to say that my earthquake is going to begin in some specified random stress field. And so that's this black line. And I'm going to say that my earthquake begins here at this little dot. Now, this earthquake is starting in a region of relatively high stress. When the earthquake happens, that stress is going to be released, and the stress drives the rupture, so the rupture grows. Now, the earthquake is going to keep growing. It's going to move, let's say it moves both to the right and it moves to the left. It moves through these other high stress regions. It has a little bit more energy. That energy makes the thing keep going. But then the earthquake moves into this region over here where the stress is really quite low. So there's no stress available to be released in order to drive the rupture. So when the earthquake no longer has enough energy to keep going, it stops. So to summarize, stress drives earthquakes. If there's enough stress for the earthquake to grow, the earthquake grows. If there's no longer enough stress for the earthquake to grow, the earthquake stops. Relatively straightforward. Now we have to deal with the details. So in the bottom here, I'm giving one estimate of how much energy is being provided. So at the beginning, we say, okay, in this region here, there's a lot of stress being provided because I've started in this region where the stress is uniformly high. As I rupture out, the average stress I can release goes down. Then I move into this relatively high stress region. Now I have a little more energy to release. If I move into this low stress region, I have less energy to release. And now I have 0 or less energy to release. And so in order to do this, we're going to have to specify a couple things. The first is, what does the stress field look like? We're going to run a whole bunch of simulations, and in each simulation, we're going to start with some random stress field. And in this random kind of stochastic stress field, we're going to specify it with two parameters. One is the mean, so we specify what's the mean stress on the fault. Here I've specified a stress relatively close to 0. And I'm also going to specify that this has some spatial variability. And that spatial variability I'm going to specify as fractal. And the last other parameter we're going to have to know is how much energy variability there is at short wave numbers. And so, sorry, at small wave numbers, so long wavelengths, and how much variability there is at high wave numbers or short wavelengths. And so we're going to specify parameter P that tells you how much variability there is at high versus low wave. Sorry. We're going to specify a parameter P that tells you how much variability there is at short versus long wavelengths. And all of these end up being scaled so that the standard deviation in stress is 1. We could have specified that as an independent parameter, but it turns out that it falls out when you non-dimensionalize the problem. So we have a specified stress field. And now we say that we're going to start our rupture. And let's say we start with this black region here. As we move through the rupture, the stress field is going to change. So if we started with this black stress field, later on we might have the blue stress field. Later we'd have the pink and the orange and then the yellow. Now, as this rupture propagates, you end up with these stress concentrations near the tip. So you're taking stress from here and you're moving the stress from there into the tip, or you're taking energy from this region and you're moving it into the tip. Now, in fracture mechanics, we have a really simple way to calculate that, at least in one dimension. And so we can estimate how much stress or energy there is available as a function of stress through a very simple integral. So calculating how much stress or how much energy is being provided is relatively straightforward. And our last question then is, we can take some stress field, we can calculate how much energy the earthquake can release, but now we have to specify how much energy do we need to keep going. Now, this is a highly contentious topic in earthquake physics, and a popular answer in recent years has been really actually you need quite a lot of energy or a relatively high stress intensity to keep going. And that argument is primarily based on observations, but also accounts for the fact that you have a lot of off-fault deformation, and so you might need a lot of energy in order to rupture. There is, however, a counter-argument which says, well, that's all well and good if I'm rupturing really fast and I have all of this energy to do off-fault deformation. But if my earthquake is just dying, I don't really want to do any off-fault deformation. And all I really have to do in order to keep rupturing is rupture just near the very tip of my fault zone. So I need to break this part of the fault and keep slipping here. I don't really have to do a whole bunch of off-fault variations. And so this argument would say, well, actually, I really only need a tiny bit of energy in order to keep going. So you could say, okay, I'm going to use either this large value or I'm going to use this small value. But if you use this small value, one of the things you'd notice is that over the course of this rupture, where you're rupturing and you're doing off-fault deformation, but then maybe you go through a region with lower stress, so you do less, you release less energy. But then you go around a corner and there's a lot of energy release, so you do all of this off-fault deformation. And now the amount of energy you're dissipating as a function of time is varying a lot over this rupture period. And maybe this minimum that I need to keep going is actually so small compared to this variability that we can just call it 0. Because all of these variations in K as a function of the stress field I'm propagating through are in fact much bigger than the minimum I need to actually keep going. And so for the purposes of making my life as simple as possible, we've gone ahead and used this last concept. And I'm going to argue in these models the rupture is going to keep going as long as the stress provides any energy at all. It's just going to keep going. And when the stress is no longer able to provide any energy to either tip, the rupture will stop. Okay, so now we are building this sort of rupture model so that we can examine earthquake likelihood, right? So what we want to do is we want to take this really simple model and we want to run lots and lots of simulations and see which fault conditions and which fault properties give rise to earthquakes and what those earthquakes look like. So here I'll show you results from about 100,000 simulations, and that takes a few hours on a laptop. Now, in each of these simulations, we specify a mean stress and a wave number decay parameter. We use those specified parameters to generate a random stress field, and then we attempt to start a rupture. Now, if we look at if the rupture grows, specifically, I'll say, does the rupture grow to at least 10 grid points? And if it grows, we can look at its properties and, oh, correct my grammar. So this is our basis here, and I'll simply skip immediately to the results. So we have a whole bunch of simulations, and we want to know how many of these simulations actually result in earthquakes, and what are the properties of those earthquakes. So let's answer the first question first. How does earthquake likelihood vary with the stress parameters that we input? And this plot on the left is potentially not super surprising. It says that if you start a bunch of ruptures with a higher mean stress, ruptures are more likely to grow. So remember that this mean initial stress is specified relative to the standard deviation in stress. So here a value, mean initial stress of 1 would say that the mean stress is equal to the standard deviation in stress. And indeed, in that scenario, 90% of the ruptures, at least with this p-value of 0.5, grow to be at least 10 grid points. In contrast, if you start with a smaller mean initial stress, you have far fewer of your simulations create earthquakes. Perhaps slightly more intuitively, you also have a variation in earthquake likelihood with this stress decay coefficient P. And so what we see is that you tend to have more earthquakes when you have a larger, a faster decay with wave number. And so what this effectively means is that you tend to have more earthquakes when you have relatively more long wavelength variation. And I think that's in some ways relatively intuitive. It's saying that if I have long wavelength variations, I'm more likely to get stress concentrations that can spread to at least 10 grid points, and I'm more likely to have an earthquake. So this works relatively well. We have earthquake likelihood as a function of our stress parameters. And then we can also look at which earthquake features vary with the initial stress parameters. And so here we can also say, okay, well, what happens if I run a bunch of simulations, and some of my simulations have this relatively low mean stress, so that's in the red, and some simulations have a high mean stress, and that's in the blue. And here again, I think this is relatively unsurprising. If you have a higher mean stress, you have a smaller B value, so you have more big earthquakes. You have a higher stress drop. On the other hand, you can also think the really cool thing about running models in this approach is that we can now look at anything we want. We don't have to just look at B value and stress drop. We can look at directivity. We can look at localization and slip. And so here I've specified one parameter. So this is the width with 95% of the moment divided by the total width with 100% of the moment. So we can look at these parameters. And of course, we can also look at these parameters as a function of the stress decay parameter. And so this one says if I have a higher B value, which means I have relatively more variation at long wavelengths, I tend to have a smaller V value, so more big earthquakes, a higher stress drop. And this time we see no real change in directivity again, and we don't really see very much variation in how localized slip is. So far, in terms of our modeling, we have an energy-based rupture model that we can run quickly. So we're going to explore parameter, we've been able to explore parameter space and say how does earthquake likelihood and how do features of observations depend on the parameters of the stress field. The only catch is that all of this information comes in the form of a really long list of values. And so we basically have this table of values. And that's not particularly useful if there was an earthquake swarm and someone said, well, there was this set of earthquakes and they have this B value and this stress drop. What are you going to tell me? I'm not going to be very interested in looking up through my 100,000 values and trying to figure something out. So instead, we're going to try to do something simple and essentially do a linear regression with neural networks in order to be able to predict the simulation output and then use those networks. And so we'll, in the interest of time, I'll just tell you that we're going to build a neural network for each of these. Essentially, we're doing a linear regression between the input parameters and the output, or a nonlinear regression, I suppose, is the key parameter here. We're doing a nonlinear regression between the mean stress and the decay coefficient and the likelihood of rupture. When we do this, we end up being able to simulate something like this, mimic something like this. And so this is one estimate of earthquake likelihood as a function of mean initial stress. The dots here are simulation results, and the lines are oh, actually, I've gotten that backwards. Anyway, so we're comparing the models for the simulation results. The biggest challenge here is calibrating the uncertainty. So we end up having to figure out a relatively robust way in order to allow uncertainty in this neural network, which involves considering the fraction of ruptures in the sets of held out simulations. And so this is one approach to doing this so that we don't have to rerun a whole bunch of simulations, but we can allow for uncertainty in our networks. So we have a neural network that can mimic earthquake likelihood. We also have neural networks for observable features. And so here we are going to do a nonlinear regression between the input stress parameters and the distribution of ruptured width. The nice thing about using neural networks is that we can predict distributions of parameters. So for instance, in this case, we want to predict, given input mean stress and decay coefficient, what is the distribution of rupture width? And so here, this is the width distributions for these two input parameters. And you see the blue is the observations. It's sort of a power law. So we've approximated here as a power law. But I think the big challenge is trying to figure out how accurately we can model this distribution. And we can indeed reproduce the approximate power law distributions that match these. And so the next challenge is to decide whether or not a power law is good enough or whether or not we need to make it different. So for width, if we often may want to use a power law distribution. For things like stress drop or log stress drop, we can do something relatively simpler. And so here we're going to say, what's the distribution of log stress drop? And we're going to, again, do a nonlinear regression between the input stress parameters and the distribution of stress drops. And so here's the stress drop distribution for one set of input parameters here. And here's our network prediction. So our network prediction is doing a reasonably good job. It also does a reasonably good job at predicting the average stress drop as a function of this mean initial stress. So this seems to be working relatively well. It's relatively straightforward to try and match the simulation results and build a neural network that can go back and forth between input parameters and observations. The next step, though, is actually using this. And so just to summarize, we'll give you some idea of what the goal is. So the goal is to say, let's see if we can take some properties of earthquake distributions. We're going to use our featural neural nets, so go back and forth between the observations and the fault properties. So we get these fault properties and we're going to feed them into an earthquake likelihood neural net and estimate earthquake likelihood, and then assess model appropriateness. And so the next challenge is, so far we've done one, and we've built these these neural nets that can go backwards and forwards. And our next step is to be able to actually invert these fault properties and use the neural nets to go back and forth. So we're trying here to build a generalized physics-based earthquake forecast. And what I've said is that in order to do this, we need to know the physics. We need to map between these fault parameters and the potential observations. And in the past few minutes, I've shown you some progress we've made in trying to use a really simple model in order to map back and forth between these. And so I would argue we have a computationally driven proof of concept that says that we can, in fact, go backwards and forwards. The other thing that we're going to need, and that I want to spend just a few minutes talking about, is how we can start also thinking about the observations that we need and that we can use to constrain the models. And so we have this really long list, and we're going to need to be able to make these observations really fast, really robustly. And so the real advantage of all of these modeling-based forecasts is that we can predict a really wide array of observable features. So we can predict moment, stress drop, directivity, stress concentration. We can predict maximum slip. We can predict early onset. And so we're going to actually want to be able to observe these. And if we're going to think about these in terms of forecasting seismicity in induced settings or in the context of slow slip events, and that's where physics-based earthquake forecasting is really important, we don't have months or even days necessarily in order to go back to the drawing board and think very carefully about this. So we're going to need to have some relatively semi-automated way to come up with these observations, and we're going to have uncertainties in these observations. And so when thinking about this, I want to ask, what sort of observations can we make, and how can we make them faster? And so I'll focus on seismicity here. So what features of small earthquakes can we observe? And if we think about what can I possibly know about small earthquakes? And the answer is actually really a lot, right? We can know things like moment, corner frequency, and directivity. These are relatively common. We can also know things like coherence, fall-off frequency, maybe pulses. We can compare with other events. We can look at maximum acceleration, displacement, radiated energy, or some features of onset. So I'll show you 3 sets of observations, so coherence, onset, and radiated energy, that students in postdoc in my group have been working on. Now, the first observation that we're trying to get faster is an approach to looking at interstation coherence. And the approach here is essentially another way to estimate the earthquake diameter, and estimate earthquake diameter. And what it says is that if I look at multiple stations that record an earthquake, if I look at those 2 stations and look at the records of energy being transmitted from the rupture area, I'm going to see different things at different stations. And in particular, I'm going to see more differences if I look at higher frequencies. So if I stand back and squint, I might think that this south and north look the same. But if I look in detail, I'm going to be able to see the differences. And if you think about this carefully, you should be able to convince yourself that you're going to need to look at higher frequencies to see the differences if you look at smaller earthquakes. And so Chris Adiastra has been looking at some of these observations and trying to use these to calibrate models and to automate them a little more. And so some of his recent work, he's been looking at observations in ridge crest and comparing them with corner frequency observations. And he's been developing the tool to say, okay, well, if I look at the differences between stations, how big do I think my earthquake is? And so you can estimate coherence fall-off frequency for various earthquakes. And he's been comparing these with the corner frequencies from others' amplitude analysis. Now, it turns out if you want to automate this reasonably well, or even if you just want to do it really carefully and robustly, only 5 of the 55 events actually had good enough data to be used. But nevertheless, even these 5 events put us in a position to start comparing what we see with others and also comparing those differences with rupture model predictions, we suggest that actually the model predictions are maybe getting the rupture velocity slightly wrong. And if anyone wants to play around with these, there's Jupyter notebooks and codes available on GitHub. And so now he's trying to expand it from 55 earthquakes to hundreds of earthquakes that have also been analyzed by others. So he's looking at global teleseismic events. And one progression here is that we're going to want to have better uncertainties on this, right? So uncertainties in corner frequencies and stress drops has long been highly questionable in the community and something that's been hard to come by over time. And so in this approach, Chris has been bootstrapping the stations considered in order to estimate uncertainty on the coherence and thus on the fall-off frequencies. So this is just one more observation that we can make about earthquakes, and we can start trying to make faster in order to be able to use in physics-based earthquake forecasting. So another set of features that we might want to use is some feature of the onset of an earthquake. And so this is work that was done by a former grad student, Rebecca Calhoun, who's now at Imperial. And she was also looking at a global data set, so 5,000 magnitude greater than 4 events all over the world. And we looked at a number of properties of just the very beginning of rupture. And the question is, if you look at the very beginning of this rupture, does it tell you anything about the final size? And can you use that as some estimate of the fault conditions? And so here she's estimated a number of properties. I'm just going to show you one property that we can examine. And that's how much energy is there in the first 0.3 seconds of the seismogram. Now, intuitively, you might think, okay, well, if I look at this seismogram and it starts really big, I might be more likely to grow into a really big earthquake. Or if I have a relatively complex fault, then maybe I'll have less connection between this size. Or if I have a relatively smooth stress distribution, maybe I'll have a tighter connection between these two. And what she's found is that if you look at this first 0.3 seconds of rupture, you can accommodate a few tens of percents of the variance. So you do have a significant correlation between the beginning and the final size. Now that's exciting in itself. It's telling you about something, some property of earthquake physics. And then we can also compare it with some of the models that we've been developing. And so here you can see sort of similar patterns in the model, so that we're not quantifying exactly the same parameter. So in the model, this kind of energy-based model, you say that if the early stress drop, so the amount of stress released in the beginning of the rupture, is bigger, you're more likely to have a larger moment. And so this is relatively promising. It suggests maybe we have one more tool to constrain earthquake physics and fault conditions. And remember, my goal is 10 to 100 different tools to constrain earthquake physics and fault conditions if we're going to move towards constraining the complexity of the system as it actually is. So with that in mind, noting that we want as many as we can, I'll give you just even one more tool that we can start to estimate, start to use. And that's looking at coherent power, or the energy that's radiated from some lone location on the fault. And here is just one more tool that you can use to estimate fault properties. And in this particular case, what we've been doing is a former postdoc, Hui Huang, has been going and saying, all right, well, there's this main shock, and I think there might be energy coming from a particular spot on the fault in the 10s or 30 seconds of before. So what he's doing is comparing this main shock waveform with the waveform that you see before in here, and using that to estimate how much power is coming in as a function of time. Now, in this case, Hui was able to identify 19 previously unidentified kind of foreshock sequences or earthquake precursors on the San Jacinto. And it could, of course, be used to find more precursors or to estimate radiated energy more generally, which is something I think is particularly exciting in the context of the lab observations that suggest acoustic emissions really are telling you something. So I'll go ahead and finish up there and say that we motivated this by saying that we would really like to move towards physics-based earthquake forecasting so that we can deal with earthquake forecasts in new physical scenarios where we really don't have this kind of past empirical model, past empirical set of earthquakes that we can use to go forward. But if that's going to need work, we first need to know physics, know the earthquake physics well enough to make it actually work. We have to make a model map between these parameters, observations, and hazards. And we're going to have to make enough observations to constrain the model and then know when we should throw the model away. So in this talk, I've shown you some progress that we've made both on the modeling front and on the observational front. So the observations, as I showed you, we're just trying to make more and more observations and make them with more automation. And on the modeling side, we've taken the very simplest model that we could come up with. We can run that model really fast, so run 100,000 simulations in the afternoon. We see relatively clear patterns in the simulation output, and we can mimic these patterns with neural networks. And so our next step is to use those neural networks along with the simulation output in order to invert fault properties and actually forecast earthquake likelihood. And I'm happy to take any questions. And I'll add the one last thing, that this is something that I'm certainly very excited about. And I think there's so many things to do. And if anyone wants to get involved or wants to play around with these codes, I'd be very excited to hear from you. So do get in touch.
Very much, Jess. I was profusely trying to take notes there to keep up with some of the things that you were what you were talking about. We do have one question in our Q&A box at the moment. I'll give another couple minutes for others as well. Ziad has asked, in your opinion, what is the most important observation, and is that difficult to obtain, that would make your model more accurate?
I don't think there's one. I think to me that's the point, that I think I've gotten very frustrated in some ways with developments in earthquake physics, because we end up with this idea that there's this really complex system and we're trying to isolate one feature and one observation. And at a certain point, that's simply not the way the world works. The earth is complex, and at a certain point we have to bite the bullet and deal with the fact that we have to invert everything together. So I think I would sidestep it and say the missing observation isn't a missing observation, it's a missing collection of observations being made together.
I like that. It's not limiting us in our science and where the ideas go, but it's more how we overcome and adapt for the things that we don't currently have. And is there space for us to think about, how do we capture those components that we currently, we don't have?
Yeah.
We have another question from Valerie. Valerie says, "Thank you, Jess. I was wondering if you had also explored machine learning algorithms other than neural networks, specifically not deep learning models, which may be more explainable."
I haven't. Well, that's not true. I guess we tried. I mean, I've tried random forest. I think in terms of explainable, though, it's the kind of goal of the neural networks is really just to do a regression between the simulation input and output. And so the kind of complexity and the explainability that we need, I think, is relatively low in that context. And I think the interest will be in kind of how we deal with these kind of trade-offs in the simulation output. And so that, I guess in some respects, I'm not sure that because the input and the output are both simulation results, there's not a particular need to understand the model, because
It does what you tell it to do, essentially. And I
it
think
does, yeah.
and those constraints are currently in a world filled with AI and uncertainty, you're putting something in to get something out to give further context and try and kind of build on the current understanding that we have and fill those gaps. I think that's where the richness is, and it's not
Yeah,
necessarily
and so I guess
elsewhere.
if we so I guess the alternative way to do it could have been to say, okay, well, I could build a neural net that goes straight from the simulation observations into the hazard.
Yep.
And I've rather declined to do that, I guess, because that does sidestep one understandable parameter. So in some ways, kind of building two neural nets and inverting one to get to the fault parameters is sort of implicitly including that physical modeling and explainability in it.
Yep.
Um,
Got you. Yeah, I think it makes a lot of sense, and I think there's a lot of scope and kind of remit to think about these in different ways. But I very much hope that the audience can understand, the ways in which you've chosen to do this and why, because I think that was
yeah.
pretty clear. We've got another question from our colleague Laura, and she says, "Thank you so much, Jess. Very exciting to think about all the different parameters. How do you feel about exploring some of the more geological properties and parameters, examples being roughness or fault complexity?"
Oh yeah, I think those would be great. Yeah, I think roughness is an obvious next target. In fact, I think that's fault complexity is way harder. Um, just because people haven't really quantified it yet, but I've thought about some ways. But yes, I think that that's one of the biggest gaps, and I would argue one of the fault complexity is one of the biggest gaps in our modeling at the moment. Yeah.
I
And it
think
certainly matters, right? There's no question that it matters. So
absolutely.
we do have to
It's
include it.
almost a
It's not
it's
optional.
almost a case of, okay, well, what do we have at this moment that will make this model better? As I said before, the observations that can come later on, we can feed back in, and we're not trying to do everything all at once, because, as you said, these observations aren't necessarily all there. We're just trying to use what we've got.
Yeah, and so I guess kind of conceptually, I've said I'm going to allow two input parameters because that's the smallest number that I can think of that's larger than one. Um, but obviously the end goal is to be able to extrapolate this to have lots of different
Yeah,
lots of different inputs and things like that. And
absolutely.
one of the things I would say, and when we think about these models and people who've done kind of past fault slip simulation models, one thing that should make you a little bit optimistic is that kind of trade-offs between two parameters very rarely give this really complex rough distribution. They often give a nice kind of smooth variation from stable and then a sort of transition to unstable. And so in some respects, while you do have to include everything, the distribution you're trying to model, we don't expect it to be chaotic. We expect it to be relatively well ordered. So there is hope. Um,
I think so. I think you've got a very good way of giving us hope as well, that the upcoming future scientists have something to work with. We have another question here. Can we use INSAR data analysis for physics-based earthquake forecasting?
yeah, for sure. I think there's kind of a variety of ways to think about that. One of them is kind of the kind of long-term rate. So can you think about spatial complexity and slip? Um, another is kind of yeah. Anyway, the short answer is yes. There are loads of predictions. So we can think about long-term slip rate, aseismic slip on the fault,
Yep,
fractal distributions of slip in earthquakes, um, variations in pore pressure, groundwater, all of these things. I think are very much
absolutely.
targets that we could build into the models.
So we've got a few more, so we'll go through these in the limited amount of time that we've got. So again, thanks for the presentation. Speaking of observation data as a model constraint, do you think it's possible to model a fault that has very limited earthquake records? For example, maybe only one event that has a magnitude 4.7, while modeling its potential maximum magnitude based on its geological and seismological parameters like fault length, slip rate, published on an official map. So that question's there's quite a lot of detail in there. So
That's
I
quite detailed. That sounds like somebody has a particular fault in mind. The
absolutely.
the yes, I guess right. So in some ways, that's the goal, to be able to say, I know something about how earthquakes work, and I'm going to build a model that's physically plausible and that makes sense, and then I'm going to say, okay, well, these are the observations that I have. Given those observations, this is the likelihood. And I would say if you have a magnitude 4.7, you probably actually have a lot of magnitude ones and twos. You can think about background seismicity rate. You can think about variations in seismic wave velocity, all of these other parameters. The challenge, of course, is whether or not you have enough observations. And of course, the challenge is whether or not this model is going to be predictive enough. So there is the possibility that we can do all of this physical modeling, and it will turn out that my intuition from 10 years ago was correct. And the Earth is just so complex that it's impractical to make any statistically valid, you can make a forecast and you can get the uncertainty right, but it may be that the uncertainty is so large relative to your forecast that it was a waste of time. Um, and I guess that's a waste of time that I'm happy to spend years on. And I think
I
it would be
think
worth it.
it's such a full circle there that well, we are doing the science to to then open up and explore more questions that come with our research. And I don't think there ever will be like a singular box that fits into. And, I do think this person probably has a fault in particular in mind. And as you said, the background seismicity or the lower recordings probably do play a large role in that. And I suggest this person probably, yeah, reach out to anyone in
Yeah,
COMET
do
with your
it.
questions. If you've got fault specific, there's someone who's bound to know a little bit more. So we've got two more here. And again, it's kind of following on from the last. How many minimum observations to model an earthquake forecast? So how well can this earthquake likelihood model that you're talking about estimate the likelihood of large magnitude earthquakes with minimum observations?
Oh, I don't know yet. Yeah, unfortunately. Um, uh, Yeah, no, so that's the bit that we haven't done yet, right? So right
That's the
now
next
we've
bit.
built the forward model. We can see the patterns in the simulation output and we can mimic these so that we can make it useful. But we haven't
Absolutely.
actually yet taken the step of inverting for fault properties and doing the forecast. So once we
That's
take
that's
that
some
next
hefty
step,
work next.
then oh yeah, that's the question that I would love to answer, but we're not quite there.
Come back next time for that question to be answered, I think. Guess I'll have the answer for that soon, I suspect. Final question here. So, thank you again for the presentation. I'm with you in the idea of isolating a few crucial parameters. What is the constraint for the number of model parameters so that it stays simple, but it's not too many parameters that it then becomes too complex? Where do you think that boundary sits?
Uh, I think so. I would go with like 10 to 100 parameters and 10 to 100 observations. And that number is based on kind of what I've seen people, is based on making lists like this, right? So you could sit down yourself and start asking, okay, well, how many statistical properties do I need to describe a fault? And however many properties you think you need to know, then that's how many observations also that you need to know. And I think that number is probably for a kind of confined system is somewhere in the 10 to 100 range. If you start to talk about a region where hazard is varying strongly spatially, then you could certainly expand that number.
Absolutely. I think it's a very typical saying of it's a can of worms, how long's a piece of string sort of thing. It's very much dependent on the scenario that you're looking at, the area, the regional geology and whatnot. And these parameters, as Jess has mentioned throughout our talk, they are very complex and we don't necessarily have all of the current observations for those different parameters and these models are built with what we currently have with hopes that they can be enabled to be better in the future with what we get. So I think that might be us. Thank you so much for everyone for attending our webinar today, and big thank you to Jess for taking time to talk us through our work. If anyone has any suggestions or recommendations for people for our next couple COMET webinars, please do let us know. But again, big thank you to Jess, and this will be made available to rewatch on the COMET YouTube channel. But thanks again, and we'll see you next month for our next webinar.
Thanks very much.